So let's formulate and then solve an aggregate planning problem as an optimization problem. As a reminder, there are 5 steps to formulating and then solving. I want to emphasize the first 4 steps are formulating, which is required before you can solve your optimization model. And we'll walk through each one of these steps in an example to solve an aggregate planning problem. Let's first remind us, what does an aggregate planning problem do? Again, it's a planning problem. So we're stepping a little bit away. So sometimes in manufacturing, like 3 months to 18 months out, and we want to make sure we're prepared to have the resources we need. It's sometimes called aggregate because we're using an aggregate units. We're at a tactical level, not an operational level. And so what do we want to understand? And what do we want to do? Well, we basically want to determine what is our planned production, what are our planned resources, how much do we want to inventory, how much labor do we want to plan to have, etc. And we'll do that using an optimization model. So what are we going to have as inputs would be things like how fast, what is our throughput rate, how much workforce size do we have, what's our current inventory level. As an input, we have the forecast. So we are building an aggregate plan to a forecast. So an input to an aggregate planning problem is a forecast for each period in our planning horizon. And we also understand, what enforces constraints in terms of capacity in our system. That may be people, that may be equipment, that may be materials. All of that gets thrown into our optimization model, and out then comes our aggregate plan, which again is per period in our planning horizon. For example, how many things do we produce? What is our workforce size, inventory, subcontracting, back orders, etc. So the first step of formulating an optimization problem is to define the decision variables for our problem. As a reminder, the decision variables are what the model can change. These are things we want to figure out what the optimal value should be. So we're changing those in a way to influence performance. We need to also make sure we properly define them so we don't have any dangling subscripts. And so here are some example decision variables. As you do an aggregate plan, you may have some of these that aren't on this list. You might not always have these. So I want to emphasize these are examples of some types of decision variables you may have. So let's think of having a planning period from period 1 to the end of the planning period. I then could have, for example, a decision variable is, what's my workforce size for month T? So if my planning period is 6 periods long, I would have 6 decision variables. I'd have, what's my workforce size for month 1, month 2, month 3, all the way to month 6, right? That's an example decision. So we could change how many people I employ each month. We could also think about hiring and firing people. And so if we're going to change our workforce, a modeling trick is to keep track of how many people we hired at each month. And we're going to denote that with H of T. Again, this isn't always a decision variable, but it could be. If you also can lay off employees, that could be a decision variable. So the number of employees laid off at the beginning of month T. And as we'll see in our constraints, if we're allowed to hire and fire people, our workforce size would be a function of what we do. So if you change H or L, that should change W. And we'll see that enforced with a constraint. Another example decision variable, especially if you're in manufacturing, would be number of units produced in month T. Oftentimes, students will think about, well, don't we already know that? We have a forecast, we know the demand. The thing with aggregate planning is we don't have to have demand equal to production. Instead, we may decide to produce more one month and then have them be produced into inventory. We may produce less than the demand if we have inventory. We may subcontract, for example. And so it is not correct to just assume demand is set, therefore demand is set, or production is set. Production is typically a decision variable if we're doing an aggregate plan for manufacturing. If we produce more than our demand, we inventory it, so we need a decision variable to capture that. We may backlog it. So this is an example of using time as a buffer. We're going to say, hey, I can't get to you. I know you want it now. We're going to delay for the next period. We may also subcontract. So we may not produce it ourselves. Instead, we're going to subcontract it to someone else. That could be an example decision variable. And we may want to know, how much extra time. So maybe overtime, Maybe this is seasonal workers. You could think about different things, but you may say, how many overtime hours per month? That would be on top of kind of my full-time workforce. Again, these are example decision variables. You oftentimes won't use all of them, and then I'm not saying this is an exhaustive list, but a couple things to think about. You would have one of these decisions for each period in your planning period, and that allows you to then plan across period to period to make different capacity, different inventory production, etc. So hopefully that makes sense. So my first thought question for today is, if I define the decision variable P of T as the number of units produced, my question to you is this correctly defined? Is this a correctly defined decision variable? I would say no, it is not. The reason it is not is we have what's called a dangling subscript. This T, where does this T come from? We need to explicitly state this T. So a correct definition could be number of units produced in month T. And if there were, for example, 24 in our planning horizon, there would be 24 different P of T. So January, P of 1 could be a different value than P of 2, P of 3, whatever. And so please properly define your decision variables and make sure you don't have dangling subscripts. So number of units produced is not correctly defined because you need to tell me where the T comes from. So the next thing is we would have, a lot of input parameters. Remember, input parameters are things that are set. And so these are things we don't want the model to change. And so these are just pieces of data that we're going to input into our model. And so the second step is to define all these input parameters for the problem. These should be clearly separated from your decision variable values, as these are input and not changeable. So for our problem, as an example, we have given forecast. So we're not going to decide what the forecast is. We're going to assume that's given. We also oftentimes have lots of cost information. So you may have material cost, inventory cost, how much cost does it say if I stock out or backlog, etc. And so one key thing is it is useful to make sure you know what the units are. That's helpful. You also may have kind of current state information. Like I may have that I currently have 80 employees, I currently have 1,000 units in inventory, etc. Right? So these are all example input parameters. One thing I want to emphasize in our forecast, as you can see here, that this forecast is quite seasonal, right? So it has small, big, 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 then small, small. So if I just wanted to set a really simple aggregate plan of saying, let's have as much demand for April, that would have a lot of extra buffer in terms of capacity. And so we would maybe be better performance if we can change different things up. Maybe we produce closer to the average here so that I don't have to produce quite as much there. I can hold it in inventory and etc. So that's the power of aggregate planning. So how do you define this? So input parameters, you can either just directly use the number, but it's sometimes useful to also define notation for input parameters. I want to emphasize these are not things you want the model to change. They're instead given. However, it is still sometimes useful to define notation, especially things like forecast. If I define something F of T as the aggregate demand forecast for period T, this is something I'm not having the model change. But it doesn't, if I define it this way, I don't have to write out, if I have 24 periods, I don't have to write out 24 things. Other things you may want to think about writing in notation or just using the numbers directly. And some examples are production costs, you may have labor, machine hours per unit, inventory holding costs, etc. You might also know something like, I want to plan for at most 10 hours of overtime per month or something like that. So these are all input parameters. Again, this is information needed for the aggregate plan, but the model will not change those. So my next thought question for you is that a company is interested in creating an aggregate plan and wants to maintain a fixed workforce. That is, they do not want to plan to hire or fire any employees during the planning period. And the planning period for this problem is T equals 1, 2, 3, and 4. So which of the following is correct? A, you should define your decision variable WT equals the workforce size. B, you should define your decision variable WT equals the workforce size in quarter T, 1, 2, 3, or 4. C, you should define the parameter WT of workforce size. Or D, you should define the parameter WT of workforce size in quarter 1, 2, 3, or 4. The correct answer here is D, in that you are not allowed to change this. So we want a fixed workforce size, which means it is not a decision variable. So A and B are incorrect because we don't want the model to change that. Instead, we want it to be the same. C is wrong because we have a dangling T. One way to get around this is you say it's a fixed workforce size, so you just define it as workforce size without T. That would be one way. Or you define workforce size in each of these quarters, and these are just input data, and so the input data would be given, and it would be given the same value. So D is the correct answer. So now that we've defined our decision variables and our input parameters, the next step is to define the objective function. As a reminder, the objective function is what determines how good is a solution. So this is a way to compare one solution versus another solution. And we are going to need to compare solutions. That means we need to have at least one of the decision variables being part of our objective function. So just again, as an example, one example of an objective function could be to minimize total cost in dollars over the whole planning period. And so we would minimize, if the planning period had 6 periods, this huge long equation, right? So what is it doing? It's saying here the regular time labor cost. So if it costs $640 per person and we have WT, which is our decision variable, how many people each month, this would be our regular time labor. Overtime, $6 per hour would be our overtime. And then every time we hire someone, it costs $300. Every time we lay someone off, it costs $500. And again, the letters denote our decision variable. So our solution out will set values for W1, W2, W3, W4, W5, W6. 1, 2, 3, 4, 5, 6, and so forth. And we're going to set them in such a way that we minimize this cost. And you can see this as it just keeps going. We'd also could potentially have the cost of holding inventory, the cost of stocking out, the cost of backlogs, and the material cost. And so these are, again, examples. It doesn't mean you will always have all of these in there. It depends what kind of things and what environment you have. Another note to say is your objective function should be a function of at least one of your decision variables, but it doesn't have to be all of them. However, if you have a decision variable that does not show up in your objective function, in your constraints, there should be some matching to that decision variable in your constraints. And so sometimes you will see this in capacity or production, and you need to make sure that you're mapping these things together. So my next thought question for you is, I have the decision variables. P of T is the number of units produced in quarter T. B of T is the number of units backlogged at the end of quarter T. And our objective function is given here. And my question is this a correctly defined objective function? I would say that it is not. The reason it is not is we have a dangling sum. So we don't know what the sum is, and we have dangling subscripts. So one way to correctly define this is to say, okay, I'm going to sum over the T, and I have a big set notation T. So everything in that element of that set, I'm going to sum over. That means you need to define T some other time, right? So this would have defined, let's say, the time periods in another place. Another way to do this is to say, nope, I want a T 1 to 4, and so I'm going to sum over whatever that is. But you need to make sure this is wrong because you have dangling T's, and you need to tell me that you're summing over that T and what that is, and how do I figure out what that is. My next thought question is given. So we have the decision variables, P of T and B of T, and I've properly defined my objective function here, and I have 2 constraints. I basically say that P of T has to be greater than or equal to 0 for all T. So there's actually 4 constraints here. So P of 1 has to be greater than or equal to 0. P of 2 has to be greater than or equal to 0. P of 3 has to be greater than or equal to 0, and P of 4 has to be greater than or equal to 0. That is why set notation is nice, is you can do it in one line, but it really represents 4 constraints. And similarly for B of t. As a reminder, an optimal solution is the best solution measured via the objective function. So that's going to tell me what best is. That is feasible, meaning it satisfies all constraints. So my question to you is, if I solve this kind of simple model, so just use your brain as the optimization solver, what value is optimal to set P1, P2, P3, P4, and B1, B2, B3, B4? So the correct answer here is C. So a couple of things you have to think about. A is not correct because I don't know how to set B. So a solution is a value for every decision variable. And so I don't know, A and B are incorrect because they don't give me values for all the decision variables. C is correct because I have both all the decision variable values and it's feasible. Whereas D is incorrect because if I want to set B of t equals to -1, you can see I get a better objective function, but it's not feasible. -1 is not greater than or equal to 0, and therefore D is incorrect because it's an infeasible solution. And for your solution to be optimal, it has to be feasible. So C is the correct answer. Some kind of conceptual things I want you to take away from this is that a solution has to give you a value for every decision variable you defined, and an optimal solution has to be feasible and the best that you can find, and the best is defined based on this objective function. So if you look at our optimal solution here, which is to basically do nothing, right? To produce nothing in any quarters and to backlog nothing, you may say, okay, that's not a very exciting optimal or aggregate plan. So if your optimal solution is to do nothing, one way you should think is, I likely have not constrained my problem in the correct way. So you can think about constraints. One way that constraints is they get us off of 0, 0. They make us do something. If our goal is to minimize cost and there's nothing to say to go do, we just won't do anything and our cost will be 0. So constraints force us to get off of 0. They also define the environment and like limitations about how we can set our decision variable values. So that's step 4, which is define the constraints, where each constraint has to be a function of at least one of the decision variables. Now I'm going to give you example constraints. These are by no means all constraints are exhaustive, but they're example ones. Oftentimes, many aggregate plans will have multiple combinations of these. So one is that, the workforce we have is a function of how many we hired or let go. So there's a relationship between W's and H's. So as a reminder, WT is the number of full-time workers working in period T. So if you think about how many people are working at the beginning of this month, well, it's how many people worked last month plus how many I hired at the beginning of this month minus how many I laid off last month. You would have that for period 1. You'd also have it for all the planning periods in your planning horizon. And so there would be 6 separate constraints here. And again, the reason we need this is in our objective function, if it costs something to hire or fire someone, which usually it does, if we don't have this and we only use W, we will never pay for that hiring or firing cost. And so what this constraint does is it says we need to have this workforce for capacity reasons, but in order to change my workforce, I have to pay for that change. And so that mapping allows us to make sure we're properly accounting for the hiring and firing costs. Another common constraint is that we don't oftentimes have capacity in order to produce anything we want. We are usually limited in terms of capacity. And so this constraint basically says my production in a given month must be less than or equal to my capacity. And this example, you may say, okay, where are these coming from? WT, as a reminder, is the full-time workforce. As you can think about, these are, I'm able to make 40 widgets or units per every worker that I have. And then you may say, okay, what's going on here? This is the overtime hour. So for one overtime hour, I'm able to make 1/4 of a product. So I need 4 hours to make one product. And so this would be my capacity. This is what I'm able to do. And then P of T is what I'm actually able to do. So this is production. So I can't make any more than my capacity. And that's true for any six periods. One thing to note is this W of T over here, you want to make that bigger so that I can produce more things, right? But every time I make that bigger, that is connected to this other constraint we just defined above, which we need to then hire people potentially, right? And then the objective function, this captures the cost of all of those things. Another constraint is that we need to meet forecasted demand. Sometimes this is called an inventory balance constraint because we're basically balancing what comes in and out. But the point of this constraint is to say we want to meet forecasted demand for every period in our planning horizon. So you may think about this looks really complicated. Okay, what's going on? The key thing here is D of T is the demand forecasted in month T. That is an input parameter. So this is a piece of data. So how do we meet demand? Well, we could either produce in that month, we could have inventory left over in the previous month, or I could subcontract, right? So if you just look at the first four terms, you can think about D of T. If I had inventory left over, I could use that towards my demand. I could produce in that month, or I could subcontract. That gives me equals to D of T. Okay, that's great, but what if I want to produce extra stuff? What happens to that? Well, if I produce extra stuff, it should turn into inventory for the next period. So if you can't back order anything, you would have I of T minus 1 plus P of T plus C of T equals D of T plus I of T, okay? If you can also back order, what do you think about back ordering? Basically says last month I didn't fill demand. So in other words, this month I have to fill what I was forecasted plus anything I left from last period. And then, how do I fill those? That's through inventory leftover, production this month, or subcontracting. But if you decide this month, I don't want to make my demand, what happens is it basically reduces my forecasted demand. I can produce less this period, but then I have to pay for it in another period. And so these are sometimes called balancing constraints because you're making sure what comes in this period equals what goes out, and you're balancing these things out. A kind of simpler constraint is sometimes you only have a limit on how much overtime you can plan for. So again, remember we're doing aggregate planning, so we're planning for this. You may say at most I want 10 hours per worker per month in overtime. You have to be careful here on how the constraint is worded in the context of your problem. What is enforcing it? So this one is a function of the total number of full-time workers, but sometimes it's just the total number. And so there are different variations on this. And then all of our decision variables have to be non-negative. You can't have negative workforce, negative hiring, etc. So those have to be greater than or equal to 0. So again, these are example constraints. They're not all of them, but hopefully they give you a flavor for what's going on. So my next kind of thought question for you, for this equation that we need to meet demand, also known as inventory balance constraint, how many constraints are defined above? Is there 1 constraint, 2 constraints, 6 constraints, or 12 constraints? The correct answer is C. There is actually 6 constraints because we have a constraint for every T, 1 through 6. So I could write this out. I of 1, so I of 0 plus P of 1 plus C of 1 equals D of 1, blah, 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 blah. And then do this for I of 2, et cetera, et cetera, et cetera. Using this kind of shorthand, I have 6 constraints, but I want to emphasize there are 6 separate constraints. We have this constraint for each period in the planning horizon. And when we implement this in a solver, we should emphasize that we are enforcing 6 separate constraints. So my next thought question is, which constraint correctly enforces the workforce relationships between hiring, firing, and workforce size in period T? So the correct answer here is B. B is the correct answer, which basically says in the current period, how many people do I have? Well, it's how many people I had in the previous period plus how many people I hired minus how many people I laid off. And this is correct. There's no dangling because I said in period T, right? So B is the correct answer. So now we have formulated our optimization problem. Now we need to solve it. Okay, so that is to implement our actual formulation and solve for the values of the decision variables and objective functions using your favorite optimization solver. So here's an example solution that I solve for my decision variable value. So now I get an actual value for H of t, L of t, W of t, and so forth. So these are the actual values for decision variables. They're optimal. We use the solver to get them. And once I plug in all of these numbers into my objective function, I get that it cost me $422,660. That's the minimum cost for this example with this specific input data. So that's actually solving the problem. We finally answered, how many should I produce each month? How many should I contract? How much should I stock out? How much should I have in inventory, etc. If we plot these things, and as a reminder, D of t is the input parameter, so that's not something we solve for, that's a given, but it's helpful. As you see, D of t changes over time. And so if I just plot D of t, which is the demand in red, how did I, answer my question of how am I going to meet forecasted demand? If you look at this, for this example, the pink line is production, and you can see you have a flat production. So how were we able to have flat production? That's because I built up inventory. So here's a lower demand. I built up some inventory, and then used some of it to fulfill demand, right? But then all of a sudden here, my demand is more than my production. And so I also need to stock out and do some subcontracting. And then here you can see my production is actually greater than my demand. So I'm inventorying a little bit there. So how did I actually get this answer? We're in this class going to use Excel Solver. However, there are many, many different optimization solvers. And in fact, IBM and Cplex and Gurobi are really state-of-the-art, much, much more sophisticated optimization solvers than Excel Solver. There's also open source. CoinOR is one example of that. Why are we using Excel Solver and not these more powerful ones? In this class, we're going to be modelers. We're going to focus on modeling problems. But please be aware that Excel Solver is limited in terms of solving. So for the problems we're going to do in this class, it gives you the flavor of formulating and then going and solving. If you have a much larger data set, IBM, Cplex, Gurobi are highly recommended. What I will say is formulating the problems, once you're able to formulate them, most of these have some sort of wrapper where you can input the formulation into something like Opal that then talks to Cplex and solves that. So as I said, in this class, we're going to use Excel Solver, mainly because this class focuses much more on the modeling side than the solving side. But there are some tips if you haven't used it. First of all is you should segregate your decision variables. It's also useful to think in matrix algebra, so columns and rows. So it is important to kind of set up things, and we'll do an example in class in kind of matrix algebra. The other thing we're going to use a lot of is what's a function called sum product, which is basically the dot product of something. So when we think about our objective functions, they're linear combinations of our decision variables and coefficients. So what we're going to do is multiply, let's say, W1 times the coefficient plus W2 times the coefficient plus W3 times the coefficient. That's basically what sum product does. It does the dot product. And so this is something we'll use a lot in Excel Solver. So what we will do is we will click, you go to the data tab and then solver, and this kind of framework will show up. And if you see here, it says, we should set our objective function. So literally what you do is you click the cell where you have your objective function. And then it says here, do I want to maximize, minimum, or do a value of? So for this example, we say minimize, and then by changing variable cells. So here, you would specify what are your variable cells. And then it says subject to the constraints. And so here you can see it has a left hand, right hand side. And so if you click here, that would be, I'm going to specify this side must be less than that side. for example. And we'll go through an example in a follow-on video. And then you can click solve. And it will then give you the optimal solution if it can find one. One thing to note is that there is this option button over here. And Excel Solver does have some limitations, especially if you have lots of data. Also, if you have sometimes very large demand values. And so here it provides a constraint precision. Is sometimes it'll be 0.00001. If you make it a little less precise, you can sometimes undo if you have a problem with nonlinearity. So again, this is a way to kind of work around some of the limitations with Excel Solver. If you're doing this in a company and you have lots and lots of decisions to make, hundreds of decisions to make, Excel Solver will not be able to do that. Instead, you should use Gurobi, Cplex, or other kind of more sophisticated solvers. If you're new to Excel Solver, there's lots and lots of YouTube's videos on this. We will go through some in this class, but be aware there are some these are extra resources. So that's the last slide in this lecture about aggregate planning. And so what should you be able to do? You should know the purpose of each of the components of an optimization model. That's an objective function, decision variable, parameters, and constraints. You should be able to formulate an aggregate planning and then solve it and realize that these are two separate things. And you should understand that.